Okay, so now let's look at the final category of optimization algorithm that we're going to talk about this week, and that is derivative-free optimization, or zeroth order optimization, or black box optimization. So again, this is the case where we want to optimize a function for which we can't even compute the derivative. I'm talking about a couple of different methods for these. Again, this most often comes up in the case where we want to figure out the best value of a hyperparameter for a model, for example, the regularization weight. And often we're trying to optimize this on a validation set. So generally, we don't even want to be, like, even if we could imagine computing the derivative of our regularization weight on our training set, generally we don't want to compute the derivative with respect to the validation set, because that would be directly optimizing on the validation set, which would be essentially putting that validation set into our training set. So let's look at a couple of different ways to do derivative-free optimization. The simplest is grid search. So grid search is the case where we want to, where we just give the grid search algorithm some space of points that it's allowed to look in. Let's say hyperparameter or a regularization weight values between -100 and +100. And what grids, and I'm willing to do 10 search iterations. Grid search will pick evenly spaced values in that among those options, try them all and pick the best. So again, there's no kind of iterative optimization here because we can't compute its derivative. An alternative to, so that method, grid search, is used very often in practice. An alternative to grid search is random search. So where grid search takes evenly spaced points within some space, random search also looks within some space, but random search just at each search iteration picks each one of those parameter values at random independently. Now, even though random search seems less principled, worse than grid search, in fact, in almost all cases in practice, random search is a better choice than grid search. The reason for that is very often, for example, in the case of choosing a machine learning hyperparameter, you might have one unimportant parameter and one extremely important hyperparameter, I should say, in both cases. Now, notice that in grid search, if we've done 9 iterations of grid search, we've only tested 3 possible values of this very important hyperparameter. Whereas in the random search case, we've actually tested 9 different values of that very important hyperparameter. So if we find afterwards that, in fact, the unimportant hyperparameter doesn't matter, and the very important hyperparameter does, we're going to end up getting something that looks like this. So let's look at loss versus, let's call this theta 1 and theta 2. If we look at it, if we look at the loss with respect to theta 2, we're going to get values that are all over the place. There's sort of no correlation between theta 1 and theta 2 because all the variation in the loss is driven by theta 1, not theta 2. Whereas if we look at the loss with respect to theta 1, it might look like this. That is, there's some very specific point that we want to pick for theta 1 to give us the best value. Now again, notice that in grid search, we would only get 3 points on this line, which would give us a much less precise estimate of what theta 1 we want. So I would say, in practice, if you're doing this kind of search for hyperparameters and you don't want to use one of the more sophisticated methods I'm going to talk about next, random search is a really good choice, even though it feels weird to leave which parameters you choose up to random. Now, the third category you might call model-based derivative-free optimization, and there's a huge literature on these, a huge number of possible methods, each of which applies in, has been used and shown to be effective in various scenarios. They include evolutionary algorithms that kind of aim to mimic how evolution works in biology. That is, they have some set of models and they take the best ones, they maybe find some way to mix them together, and then try those other models and do that across many iterations. Another very widely used one is called simulated annealing. We're not going to talk about that. The kind of, I would say, trendiest method that's used these days is you can call Bayesian regression or Bayesian optimization. This aims to fit some approximate function based on the values you've tried so far, and it takes the derivative with respect to that surrogate function, that is, that function is estimated, and uses that to pick which value to try next. But again, there's a huge literature of these methods, and generally, just to be clear, generally optimization in this derivative-free case is much, much harder than in the gradient case, the case where we can, in fact, compute a gradient over our objective function, our log likelihood function.